Hello everyone, this is Anjani Sai Sudhir, roll number 20 BQ1A4702 of CIC section. Today the topic is about wave optics. Interference is a natural phenomenon which occurs in an environment. Superimposition of two waves with the following conditions at same frequency traveling in the same direction. Phase difference remains constant with time. This is called interference. Intensity is not distributed uniformly in the space. The non-uniform distribution of energy into superposition of two waves is called interference. At some point, the intensity is maximum and the interference at this point is called constructive interference. And at some point, the intensity is minimum and the interference at this point is called destructive interference. Here are the examples of constructive and destructive interference. In constructive interference, wave A and wave B traveling in same direction, having same frequency and amplitude are superimposed each other. Here, the phase difference is either 0 or pi. So, the waves superimposed resulting in the formation of constructive interference, that is wave of A plus B, having double the amplitude. This constructive interference results in the formation of bright fringes. In destructive interference, wave A and wave B are also traveling in same direction with same frequency, but the phase difference is pi by 2. So when they are superimposed, the resultant amplitude will be 0. Destructive interference results in the formation of dark fringes. Coherent sources. Coherent source. Two sources are said to be coherent if they are same frequency, same wavelength, same amplitude production of coherent source. Constant phase difference with time. Here, this Young's double slit experiment performed by Thomas Young, who invented interference. Here, the S is a source in first screen which emits a wave into second screen which has two slits, namely S1 and S2. They are superimposed and finally the waves are on the screen which result in the formation of maxima and minimum intensity fringes. Maxima is a bright fringe and minima is dark fringe, that is alternative bright and dark fringes. Phase difference and path difference. If the phase difference between two waves is 2 pi, then path difference between the two waves is lambda. Let for a path difference x, the phase difference is delta. We know that for a path difference lambda, phase difference equal to 2 pi. So, for a path difference x, the phase difference equals to 2 pi x by lambda. So, phase difference delta equals to 2 pi x by lambda equals to 2 pi by lambda into path difference. Thin films. Here in this diagram, PQRS is a thin film. AB is an incident ray on PQ, that is a first level. Mu1 is the refractive index of air, mu2 is the refractive index of the glass. BD is the refracted ray and BC is the reflected ray. I and R are angle of incidence and angle of refractions. When the refracted ray is imposed on RS surface, it is then again reflected back to the first surface, that is DE is the reflected ray, and then EF is the refracted ray outside. T is the thickness of the glass sphere. Now consider triangle BDH and DHC. Those two are similar triangles. From the experiment, delta B equals to BD plus DE into mu2, that is refractive index of the glass, minus BC into mu1, refractive index of A. From triangle BHD, cos R equals to HD by BD, that equals to T by BD. BD equals to T cos R. Tan R equals to Bm by T. Bm equals to T tan R. From triangle HCD, cos R equals to HD by D, that equals to T by D. dE equals to T by cos R. Tan r equals to He by T. He equals to T tan r. From triangle BCE, sin I equals to BC by BE equals to BC by BH plus HE equals to BC by T into tan r plus T into tan r. Sin I equals to BC by 2T into tan r. BC equals to 2T tan r into sin I. Multiplying with sin I in both numerator and denominator. BC equals to 2T sin I sin r by cos r into sin r by sin r. This implies BC equals to 2T mu into sin square r by cos r. Then delta B equals to BD plus DE into mu 2 minus BC into mu 1 equals to T by cos r plus T by cos r into mu 2 minus 2 mu T into sin square r by cos r mu 1. Mu 1 equals to 1 and mu 2 equals to mu. Equals to 2T cos r 2T by cos r into mu minus 2 mu T into sin square r by cos r. Let's name it 3 equals to 2 mu T by cos r minus 2 mu T by cos r into sin r sin square r, that equals to 2 mu T by cos r into 1 minus sin square r, that equals to delta equals to 2 mu T into cos r. Delta lambda by 2 equals to 2 mu T cos r minus lambda by 2, resultant path difference. Constructive interference. Delta equals to n lambda. 2 mu T into cos r minus lambda by 2 equals to n lambda. 2 mu T cos r equals to n lambda plus lambda by 2. 2 mu T cos r equals to lambda by 2 into 1 plus 2n. Destructive interference. Delta equals to 2n minus 1 into lambda by 2. 2 mu T cos r minus lambda by 2 equals to 2n minus 1 into lambda by 2. 2 mu T cos r equals to n lambda. Newton rings. When a planar convex lens is placed on a glass plate, a night film of gradually increasing thickness from the point of contact is formed between the upper lens and the lower lens. When light falls normally on this film, then alternate bright and dark concentric rings with their centers dark are formed. These rings are known as Newton rings. This is the illustration of Newton rings, where S is the source, G is the glass plate, L equal to planar convex lens, P is the beam splitter, M is the traveling microscope. Planar convex lens with its convex surface is placed on the glass plate. The air medium is present between the planar convex lens and the glass plate. The point of contact is formed between the planar convex and the glass plate in the air medium. The source is monochromatic, that is, the light emitted by it is a single color. The lens is placed after the source, which makes the light travel in parallels. Determination of path difference. Delta equals to 2 mu T cos r. In Newton rings, delta equals to 2 mu T cos r plus lambda by 2. Mu equals to 1, that is air index, comma r equals to 0. Delta equals to 2 into T cos 0 plus lambda by 2. Delta equals to 2T plus lambda by 2, where T is the thickness of air film, lambda is the wavelength of monochromatic light incident on the lens, delta is the path difference, and mu is the refractive index of medium. Determination of thickness of disc. From diagram, OA equals to Rn, OB equals to Rn, OD equals to T, OC equals to 2r minus T. Let. From circle's property, horizontal diameter equals to vertical diameter. OA into OB equals to OC into OD. Rn into Rn equals to 2r minus T into T. Rn square equals to 2RT minus T square. T square is neglected. Then T equals to Rn square by 2R. Now let's say thickness is delta. Delta equals to 2 part difference equal to 2T plus lambda by 2. Delta equals to 2 into Rn square by 2R plus lambda by 2. That equals to Rn square by capital R plus lambda by 2. Dn equals to 2 small rn. Rn equals to dn by 2, that is diameter by 2. This implies Rn square equals to dn square by 4. Now the part difference equal to dn square by 4r plus lambda by 2. Constructive interference. Delta equals to n lambda, that is dn square by 4r plus lambda by 2 equals to n lambda. Dn square by 4r equals to n lambda minus lambda by 2. Dn square equals to 4r into n lambda minus lambda by 2. Dn equals to square root of 4r, 4 capital R lambda by 2 into 2n minus 1. Destructive interference. Delta equals to 2n minus 1 into lambda by 2. Dn square by 4r plus lambda by 2 equals to 2n minus 1 into lambda by 2. Dn square by 4r equals to lambda by 2 into 2n minus 2. This implies dn square equals to 4r lambda into n minus 1. Dn equals to square root of 4r lambda into n minus 1. N minus 1 is neglected to n. This implies dn equals to square root of 4r lambda n. Applications of Newtoning. Let dn is the diameter of nth ring, dn plus m is the diameter of n plus mth ring, n is the number of rings, and lambda is the wavelength of light. R is the radius of curvature for convex lens. dn square equals to 4 lambda nr. dn plus m square equals to 4 of n plus m into lambda r. Let's limit equations 1 and 2. Now 2 minus 1, that is dn plus m square minus dn square equals to 4n lambda r plus 4m lambda r minus 4n lambda r. This implies dn plus m square minus dn square equals to 4m lambda r. This implies lambda is equal to dn plus m square minus dn square by 4m r. Determination of radius. Dn square equals to 4n lambda r. Dn plus m square equals to 4 of n plus m into lambda r. Let's name it equation 1 and 2. Now 2 minus 1. dn plus m square minus dn square equals to 4m lambda r. R equals to dn plus m square minus dn square by 4m lambda. Determination of liquid refractive index. Let's dn square equals to 4n lambda r, say equation 1. dn plus m square equals to 4 of n plus m into lambda, say equation 2. Now 2 minus 1, that is d square dn plus m square minus dn square equals to 4m lambda r, say equation 3. This is for air medium. Now consider dn is the diameter of nth ring in air medium. D dash n is the diameter of nth ring in water medium. dn plus m is the diameter of n plus mth ring in air medium. D dash n plus m is the diameter of n plus mth ring in water medium. Mu is the refractive index of air, that is equals to 1. Mu dash is the refractive index of water medium. Lambda is the wavelength of light, and r is the radius of curvature for planar convex lens. Similarly, d dash of n plus m square minus d dash n square equals to 4m lambda r by mu dash. Let's say equation 4. This is for water medium. Now let's divide equation 3 with equation 4. This implies dn plus m square minus dn square by d dash n plus m square minus d dash n square equals to 4m lambda r by 4m lambda r by mu dash. This implies dn plus m square minus dn square by d dash n plus m square minus d dash n square equals to mu dash, that is refractive index of water. Thank you.